Let's overload more operations. Right addition. So this overload the right hand plus operator when we have other on the left side and the tensor class or self on the right side. So we have the same type signature, and we need to return the tensor.add, but in this case we just need to change this arguments. We need to wrap as the data gate first of all other, and as the second argument we put self. And one more operator in place addition, I add, and we have the same type signature, but in place operator do not track gradients, and it's important. So we have self.data, and we implement the in place as self.data plus the tensor built-in D array other. We just sum up the data, so nothing else, and return the self. So this operation, in place operation, do not track gradients, and we just change the data and return the tensor back. Let's check these operations. For example, a plus b. Let's run this code. Okay, of course we need to initialize the tensor. Everything works fine, broadcasting works fine. We can define the tensor c, and let's compute the gradient, for our computation graph, and we can call c.backward, and we need to provide the gradient. Let's make the gradient as the numpy once like the c.data. Let's compute the gradient back. Okay, and after the debug I realized that the problem is right over here. It's pure typo, not min but max. It's very important, that we need to take the max value, not min. Let's use max. Okay, let's run this code, and let's run the computation again. Okay, we just computed the gradient in the backward mode, and let's check the b dot gradient and a dot gradient. I think that it should match with our, it's exactly matches with our example, that we used before for the manual imitation of this operation, of this transformation. And I think that we are ready to add the subtraction operation. And for this purpose, we need first of all to reload the negative operator. In this neg, overload the unary minus operator to negate a tensor. So let's use self, and we return back just the tensor data type. Okay. As the step number 1, we need to compute the output, and it equals negative self dot data. So dependencies, list, and if the self dot requires gradient, we need to add to the dependencies, append the leaf with the value as self, and the gradient function we can use the lambda, and we have gradient as the argument, and we return the negative gradient back. So it's just pretty straightforward implementation. We return the new tensor object with the output requires gradient as the self requires gradient and dependencies list. Nice. Then we are ready to overload the sub operator, and we can copy because it's approximately the same type signature, and we now can use the combination of negative and add. We can return the self plus the negative tensor dot data gate of the other. Okay, and it would be absolutely, yeah, I think it will be absolutely the same result. So then we can overload the right sub, and we can copy type signature, yeah, and the body of the previous function, but in this case we need to use the tensor data gate plus the negative self. We just swap places, yeah. And the last one, the last piece is the in place sub. Okay, and we have the same type signature, but we need to use self.data because, as far as I remember, the in place operations do not track the gradients. It equals the self.data minus tensor build and the array from the other and return self. So we have no any gradient tracking in this method. And for example, right now we are ready to let's say C minus A. We have this operation minus B. Yeah, it works pretty nice, yeah, and plus C. And the next operation is multiplication. And multiplication computes the element-wise product of two tensors. You can see how it looks from the mathematical perspective. We have the function with two tensors A and B, and we multiply them element-wise. That's quite simple. And the derivative of such operation with respect to A and B is on the screen, yeah. With respect to A, we have the B as the result, yeah, accordingly with the school grade calculus rules, yeah. And with respect to B, we have A as the result. So let's implement such an operation. I think that we can copy it and rename it to multiplication. So instead of the addition, we need to replace to the multiplication. And I think that output is totally correct now. Requires gradient, the same, yeah, everything looks nice. Dependencies, yeah, same mechanics. But I think that it's pretty similar logic, yeah. We, for the backward mode, returns one or the other item. And I think that we can define the backward method, and we receive the tensor A and tensor B in the backward. So, and we need to define inside the closure of the backward the method backward. And for the backward, we have just the gradient as the numpy and the array. We return back numpy and the array. Let's follow the calculus rule number 1 with respect to the variable A. And the gradient in this case equals the gradient times the variable B. And we need variable B, and we need to return the tensor dot backward broadcast and we put the tensor A as the original tensor, and we put the gradient, the computed gradient on this stage. So it means that we have gradient on this level. We compute, we append this data to the gradient that contributes to the final output. But for the broadcasting, we use the tensor A, because we compute the gradient with respect to tensor A, as you can see in this formula. So it means that this backward works fine in first scenario, but in case if we just put the arguments in backward mode, first of all we define the tensor B and the second argument is the tensor A, we just swap the argument and it's exactly the second option. I can show you how it works. We have this first case for A, in case if A requires gradient. We use the value tensor A and gradient function. We can utilize the backward and put the arguments as it is, like A and B. So in this case we compute the backward mode with respect to the first variable, to the variable A. But for the second scenario, we can swap places for the arguments B, A. And that's exactly what we need. We have the second scenario. And I think that this implementation looks nice. We can copy this multiplication and put it right over here. Let's align the code and define it as the static method. Okay, and the only thing that we need to fix, we need to return the backward inside this backward method, because we have this backward function inside the closure of the underscore backward. And I think that now we are ready to overload the same triple of the operators, but in this case it's multiplication. And we need to use tensor.mul for the self and tensor datagate other. Then write multiplication and replace the multiplication here. And in place multiplication, it's exactly the same logic, but we need to replace this plus sign. And I hope that we are ready to use multiplication, and it works fine. We can multiply C times A. It looks nice. It works. Okay, and now we have one more operator. We have minus, plus, and multiplication in our tensor, and it works nice. And we can build a small experiment. We can add one more variable D for this bunch of operations and compute the backward and put the gradient as the bunch of ones. And you can see that everything works fine. Everything looks nice. We have the gradient for the tensor A and gradient for the tensor B. So the dimensionality, the broadcasting, and everything else we need works fine. No problem at all. Let's add one more B, and you can see how it changes the gradient. So everything looks nice. Broadcasting and everything else we need works fine. No problem at all. Let's add one more B, and you can see how it changes the gradient. So everything looks nice.